Okay. So as we're going over this one, this is a function of log base 2 to the x, and it's really helpful to think about it as an inverse. So I've put down the function y equals 2 to the x right here, and y equals log base 2 of x. These two are inverses of one another. And so if you look at this dashed one here, this is the graph of y equals 2 to the x. It has a horizontal asymptote at y equals 0. It has a domain of all real numbers. It has a range of y equals 0. And so if we look at this function with a log, it asks you what value of x would produce an output of -5. And how do you know? That would basically be what power, if I raise 2 to the power of -5, that's going to give me 1 over 32. And then it's asking you for the domain and range of that function. So if you plot these points, this is what it's going to give you. And if you plot those points together, you might notice that there's also an asymptote, but this time it's a vertical asymptote. And the equation of that would be x equals 0. And then it's going to go towards infinity here. So if you look at these graphically, if you plotted the line y equals x, these two are kind of like mirror images of each other across that line, which is, again, one of the properties of inverses. So with inverses, graphically, it's going to be reflection across the line y equals x. The table, you can see that you've just simply switched your x and y's. With the equation, you've switched your x and your y's. And the other thing that switches is the domain and the range. So the domain of the log function is going to be the range of your exponential function. So the domain is going to be that x is going to be greater than 0. And then the range, you'll notice the range, the y values can be anything, which is the same as the domain of the exponential function. So your domain and range kind of switch places as well. So you can say again that they're switched. So you can see in lots of different ways this log function is an inverse of the exponential function. Any questions about that? All right, let's take a look at question 4. So we have 3 parent log functions are graphed here. What do they all have in common? So what are some things that every single parent function of a log function is going to have in common? You can give me one thing. The domain and range. What else? The asymptote. They all have a vertical asymptote of x equals 0. There's one other thing that I think is pretty obvious as well. Danny. The x-intercept. They all pass through that point 1, 0. And so what's different about them is, again, kind of like the rate of growth, how much they're kind of changing. But otherwise, they're going to have that same generic shape. So kind of like an exponential function is always going to kind of go like that, unless it's decay, of course. But the log function is going to have a similar kind of look, but again, just reflected over that line y equals x. It's going to have a vertical asymptote, and the parent's going to always go through the point 1, 0. Another point that it always passes through is this point where the x is 1. I mean, where the y is 1. Let's think about what that x value would be. So it says, if you try and match up these 3, here the base equals 10 because there's no base there. Here the base is 4, and here the base is e, which is approximately 2.7. So if you think about this, if you have the function y equals log of x, and you put in the point 10, 1, 10 is the x value, y is the 1 value, that's going to be 1 equals log of 10. If there's a base of 10, you know that log base 10 of 10 is equal to 1. So this function here has to be equal to log of x. And so this one is going to be y equals log base 4 of x, because log base 4 of 4 is going to be equal to 1. And then this one is going to be the natural log of x, because that's log base e of e is going to be equal to 1. So they also all go through the point B1, whatever the base is of your log. So that's going to be, all of the log functions are going to go through the point with the base, and then the y value is going to be equal to 1. So if we use our graph to estimate log base 4 of 6, if you go to log base 4, that's your middle one, and you go to where x equals 6, and you kind of go up to your graph here and then go across, it looks to me like it's about 1.3. And that basically means that if I took 4 and I raised it to the power of 1.3, that would be equal to 6. Any questions about number 4? All right, let's go down to number 5. This one was probably the most challenging question. And so it says we have a function y equals log base 4 of x, and we're going to move it to the right 3 units. So let's think about all the other functions that we've done before. When we do a horizontal shift, we're going to change something about where the x is. And if it's moved to the right 3 units, we're going to represent that by doing the opposite. So this would be log base 4, but instead of being x, it's going to be x minus 3. And so think about how that is going to affect your x-intercept, your asymptote, your domain, and your range. What do you think the new x-intercept is going to be? Instead of being at 1, what is it going to do? It's going to be at 4. What do you think the asymptote is going to do? Instead of being at x equals 0, it's going to be at x equals 3. It's going to shift to the right 3 units. Everything's going to shift to the right. And then the domain, instead of being x is greater than 0, is going to be x is greater than 3. And the range is still going to be all real numbers. So with an exponential function, all of these things are affecting the are affected by a vertical shift, whereas with a log function, they'll be affected by a horizontal shift. Any questions? All right, let's go on to the next page, and we're going to just take some notes up in the top box there, just to summarize what we just learned about log functions. So if you have the function y equals log base b of x, there are 2 key points that that function is going to go through. The first one is the x-intercept of 1, 0, and the other one is b1. And this is really helpful for you as you're graphing functions to really recognize those 2 points. The other thing that that function will always have is a vertical asymptote. It's going to be x equals 0. The domain is going to be x is greater than 0, and the range is going to be all real numbers. So let's just do a little sketch of what the graph would look like, and also the parent function, the parent table. And I'm going to just do this with a generic base of b. And so remember that this is just the inverse of an exponential function. So for an exponential function, what did we do? We really just focused in on those middle 3 points, and we went from our x values going from -1 to 1. And so for the log function, we're going to do a similar thing, but our y values are going to go from -1 to 1. And then our x values are just going to be the opposite of what they were in the exponential function. So this is going to be 1 over b, 1, and b. And instead of having a horizontal asymptote, you're going to have a vertical asymptote. So it's really just the inverse of the function y equals 2 to the x. Let's just draw a little sketch of what that would look like graphically. So our asymptote is going to be along the y-axis. It's a vertical asymptote. We're going to go through the point 1, 0, and we're going to go through the point B1, and then we're going to head towards the asymptote, and we're going to head towards infinity. And then once you have your parent function, you can do transformations on this just like we did with the exponential functions or any other function that we've done so far. Any questions? All right, let's do a couple of examples together. So this one's asking us to graph the function of log base 3 of negative x without a calculator and identify the following. So I'm going to start with my parent table. And this time it's log base 3 of x. So my parent table, I'm going to start with -1, 0, and 1 in my y's. And then here my base is 3. So here I'm just going to have 1 over 3, 1, and 3. And then I have a vertical asymptote of x equals 0. And I always put the asymptote in there because if it's affected by transformation, that's going to show up there as well. So let's go ahead and transform that. Again, I'm going to look in where my x is first. What's changing about my x? There's a negative. So I'm going to just, in my parent table, I'm going to now just make my x's negative. I'm going to take all of my previous x's and I'm just going to make them negative. And if I take 0 multiplied by negative, it's going to stay the same. So my asymptote stays x equals 0. That's what my vertical asymptote is going to be. And then I'm going to look at my y's. There's absolutely nothing changing about my y's. So if there was something multiplied in the front or added on beginning or end or subtracted, then I would change my y values. But in this case, nothing's changing. So I'm just going to keep my y the same. And then go ahead and plot those points. It's a little hard to get your fractions in there, but and then once you have those points, you might not be totally sure what it looks like because it might even look like a little bit like there's a horizontal asymptote. So before you do anything else, go ahead and draw in that vertical asymptote. And then once you've done that, you're going to head towards the vertical asymptote. You're never going to cross it. And then here, this is going to go towards infinity. And our x-intercept was at -1, 0. Our domain is x is less than 0. The range is all real numbers. Any questions? All right, why don't you guys take a look at questions 2 and 3 and see if you can answer those 2 questions. For question 2, you're going to be matching up these graphs. Think about what the parent would look like. Think about what transformations have occurred. and see if you can match them up. And then go ahead and try question 3. I'm going to stop recording.